All right, so now we are back at it, doing orthogonal sets. A set of vectors u1 to up in Rn is said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal. So, okay, interesting. Show that u1, u2, u3 form an orthogonal set. All right, you just take all n choose 2 pairs and show that they're orthogonal. If S is an orthogonal set of non-zero vectors in Rn, then S is linearly independent and hence a basis for the subspace spanned by S. Yeah, that's let's see how do they do the proof? We know that these all go to 0 because u1 is orthogonal to all of them. Since okay, an orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. Okay, that's cool. Yeah, we like orthogonal bases, or at least I do. The next theorem suggests why. Actually, you know what? I like unit length orthogonal bases. The next theorem suggests why an orthogonal basis is much nicer than other bases. The weights in a linear combination can be computed easily. If u1 to up is an orthogonal basis for a subspace W of Rn, for each y in W, the weights of the linear combination okay, that's pretty simple. You just to find the weight. Oh yeah, so yeah, it's faster. All right, so I actually do want to look at this example. So express this as a linear combination of the vectors in S. Oh, it's all symbolic, but they do. So C1, yeah, okay, cool. 6.2 ortho sets. If if U1 to UP ortho basis, then and Y is equal to the sum of CI UI, then it's easy to find the weight CI because we take y dot ui equal to the sum of ci ui dot ui, but or let's say uj, then all go to 0 except the one where I equal to j. So we end up we get y dot uj over uj dot uj is equal to cj. Okay, cool. An orthogonal projection. Given a non-zero vector u in Rn, consider the problem of decomposing a vector y in Rn into a sum of two vectors. Given a non-zero vector u in Rn, consider the problem of decomposing a vector y in Rn into the sum of two vectors, one a multiple of u and the other orthogonal to u. Oh, okay. Where y hat is equal to alpha u, and z is orthogonal to u. Given any scalar alpha, let z equal to y minus au, or alpha u, so that one is satisfied. Then y minus y hat is orthogonal to u if and only if that is, one is satisfied with z orthogonal to u if and only if alpha is equal to y dot u over u dot u. I knew that in the last section when they asked us to compute this stuff, they weren't just doing it for no reason. Y dot u over u dot u dot or times u. The vector y hat is called the orthogonal projection of y onto u, and the vector z is called the component of y orthogonal to u. If c is any non-zero scalar and if u is replaced by cu in the definition of y hat, then the orthogonal projection of y onto cu is exactly the same as the orthogonal projection of y onto u. Hence, this projection is determined by the subspace L spanned by u, the line through u and 0. But wait, isn't it up to some scalar multiple? Sometimes y hat is denoted proj under L, or proj onto L of y. Proj y onto L. So y hat is equal to proj y to L and then to find z, so this gives you z. Okay, cool. Oh, because you can't actually project um you actually have to project onto the span. You can't just project onto. There's no there's no way to make the y minus the line from y to u orthogonal to y. A geometric interpret. Wait, what is theorem 5? Theorem 5 is okay. If you have, yeah, okay. Alright, stay focused. The decomposition in figure 4 can occur in physics when some sort of force is applied to an object. Often the problem involves some particular direction of interest, which is represented by another vector u. For instance, if the object is moving in a straight line when the force is applied, the vector u might point in the direction of movement. A key step in the problem is to decompose the force into a component in the direction of u and a component orthogonal to u. Orthonormal sets. Ooh, that's what I'm talking about, bro. Orthonormal. A set U1 to UP is an orthonormal set if it is an orthogonal set of unit vectors, bro. Me and my homies love orthonormal sets. If W is the subspace spanned by such a set, then U1 to UP is an orthonormal basis for W, since the set is automatically linearly independent by theorem 4. Bam. The simplest example of an orthonormal set is the standard basis. Any non-empty subset is also orthonormal. Here's a more complicated example. Weird. When the vectors in an the vectors in an orthogonal set of non-zero vectors are normalized to have unit length, the new vectors will still be orthogonal. And hence the new set will be an orthonormal set. It's easy to check that the vectors in figure 6 are simply the unit vectors in the directions of the vectors in what? Matrices whose columns form an orthonormal set are important in applications and in computer algorithms of matrix computations. Their main properties are given in theorems 6 and 7. Ah, that's so cool. Yeah, that's so true. Wow, that's very nice. Okay. Let U be an n by n matrix with orthonormal columns. Let x and y be an Rn. Then the norm of Ux is equal to the norm of x. The norm of Ux dot Uy is equal to x dot y. Wait, really? That one, B is really interesting. They're length preserving linear transformations. Oh, nice. Yeah, preserves lengths. These properties are crucial for many computer algorithms. Nice. Pretty quick section, but okay, so 4 is the only really interesting one because it's kind of a proofy thing. How are we going to show that? Okay, so this one is probably an application of this theorem. This is a good problem. Show that the determinant of an orthonormal square matrix is plus or minus 1. Okay, so okay, I think I need some help with this one. So intuitively, if I can just spam my thoughts, it's that that we know from theorem, which we still definitely need to prove, but that basically U is going to be length preserving. So if we give it anything, even though that anything will change its direction, it's not going to change its length. So intuitively, because the way that I think of the determinant is you take, the way I think of the determinant is I have some linear map, probably an n by n matrix, and I send a basis, and I send the standard basis in there, and I see how that like unit cell gets stretched, particularly its like generalized volume or its volume. See how that volume grows or shrinks. But if all of those elements are going to stay the same length, it's not only that, but so okay, it's actually A and B. So you can't just, because the thing is, if they all stay the same length, but they all collapse their orthogonality, then um then it wouldn't work. But since they stay orthogonal and they're the same length, then that unit cell must maintain its volume. But let's see how they answered it. Cool. Let's see what's next. Orthogonal projections. Okay, let's do 11. Let's do 11. We're going to compute the orthogonal projection. All right, so this is problem 11. Compute ortho projection of 1, 7 onto the line -4, 2 between 0 and -4, 2. All right, let's switch over to my notebook. So, okay, so I need to actually go back to the notes because I forgot already. So I just need to draw some pictures. So 1, 7 is up here. So this is, let's let this be U. Or let's let this be Y. This is Y. This is Y. And then -4, 2. It's like right here. Maybe like right there. Just call this X. So let's just check that Y dot X is equal to 1, 7. Wait, did I write that down? Isn't it 7, 1? No, okay. Dot minus 4, 2 is equal to minus 4 plus 14 is equal to. So these are not orthogonal. Okay. So we want to write y equal to like some c times x plus z. So like to draw a better picture, maybe if we had like this and this is y and this is the line spanned by x, span x. Then we want to draw this. And then, so this would be the cx, where x is like, I don't know, we could even draw x out here like that. And we just find that c, because this is the span, and then this would be that z. And we want, and x dot z equal to 0. That's what it means for x to be orthogonal to z. So wait, the derivation is, we can rewrite this as z is equal to y minus cx. And y minus cx is ortho to u if and only if z dot cx equal to 0 equal to y minus cx dot u dot cx, and this is equal to y dot x minus cx dot x is equal to y dot x minus cx dot x. and this is z. Okay, so now we just need to do all of that. So, so we just compute, so y dot x is going to be 10, and x dot x is equal to minus 4, 2 dot minus 4, 2 is equal to 16 plus 4 equal to 20. So then we get 10 over 20 times minus 4, 2 is equal to minus 2, 1. So this is equal to y hat. This is the projection. So this is going to be like minus 2, 1. This is going to be like right here. This is y hat. This is really like it's like out here, because if we wanted to draw this, it's kind of like that. It's a bad drawing. Anyways, this is y, and this point is y hat. So is that the whole problem? Let me check. Or do we need to compute? When they say compute the orthogonal projection, okay, they don't want you to find z, but let's just find z. So now we have y is equal to y hat plus z, right? So then we can do 1, 7 minus 2, 1 is equal to 3, 6. So then 2, 3, something like this. Or rather, it'd be like over here, something like that, right? 1, 2, 3, 6 or something. And then this would be right. This, because this has to form a right angle. All right, so that's that one. Let's hop back over to. All right, so that was a good problem. Now let's see. Write this as a sum of. We just did that. This is the same thing as you compute the orthogonal projection of y onto u, and then you subtract y from or that you subtract y from that, and that gives you z, and then you write it as a sum. All right, determine which of these are orthonormal. Um, So combinations. That's a thing, right? Can I do this? Okay, great. So okay, so let's just say C's is equal to this. First of C's. So wait, if we uh okay, so let's just do a test here. Let's take the hardest. It's too hard to write these out. Let's just do the first one. So x1 equals fill 1/3 3. X2 is equal to minus 1/2 0 1/2. I just want to write the code for this. I mean, obviously we can just do dot x1 x2 and then do norm of x1 minus x2. Oh, they're not they're not. But what we can do is we can do C is equal to the combination of our vectors x1 and x2. And then so we do all wait, is there a function is unit vec. Oops, how did I do that? Is unit is equal to norm of x approximately 1. Then we say all is unit of x's and so that's the first condition. The second condition for being an orthonormal set is I don't know if this is going to work. Right, so you have to do so what you want to do is so this is orthonormal of x's is equal to combinations of x's 2. All right, so that's the whole function. Is orthonormal is all unit and all pairs orthonormal or orthogonal. So that's that function. So there you go. So now we don't have to do any of these sections because we wrote the code to do it. We didn't do the normalized part, but that's easy. I think there's already a normalized function though. All right. So true falses. Not every linearly independent set in Rn is orthogonal. Yeah, that's true. Not every orthogonal set in Rn is linearly independent. That's false. If Y is a linear combination of non-zero vectors from an orthogonal set, then the weights can be computed without row operations. Is it orthogonal or specifically orthonormal? Wait, did I switch over? Yeah, I did. Okay. Okay, yeah, so that's true. '26. If a set S has the property that false. That's just orthogonal. That's not orthonormal. If the vectors in an orthogonal set of non-zero vectors are normalized, then no, that's false. Normalization is a direction preserving operation. 28. If the columns of an n by n are orthonormal, then the linear mapping preserves length. That's true. That's true. A matrix with orthonormal columns is an orthogonal matrix. That's true. 30. The orthogonal projection of y onto V is the same as the orthogonal projection of y onto CV. That's true. If y is a line through 0, and if y hat ooh. That's false, but it's the coolest problem that we've gotten so far because it actually I'm starting to see how least squares is starting to play into this whole thing. So I'm gonna say false on that one though. Because it's not. It's the an orthogonal matrix is invertible. I think that's true. All right, so just checking our answers. Okay, true. Wait, 24 I wrote is false, but oh, not every. Oh yeah. Wait, not every orthogonal set in Rn is linearly independent. Really? Oh. The zero. Okay, that's right. Okay, 25 is true. 26 is false. 27 is false. 28 is true. 29 is false. Wait, what? 29? A matrix with orthonormal columns is an orthogonal matrix. Wait. What's the definition of orthogonal matrix? Orthogonal is, so this one's, it's defined as square invariable such that inv u is equal to u transpose. But it has to be square, and so that's why 29 orthonormal calls does not imply square. What did they say? They said also requires square, a non-square A with orthonormal columns isn't invariable. Okay. I hate that it does this renumbering. It's so ridiculous. Okay, 31 is false. Wait, 30 is true. 31 is false. And 32 is true. Okay, cool. So we just got those two wrong. But those are good. All right. All right, problem 33. Prove theorem 7. The norm of ux is equal to the norm of x. Prove that u is an m by n orthonorm call? That u of x dot u of y is equal to x dot y. And then part C, u of x dot u of y is equal to 0 if and only if x dot y equals 0. That one we don't even really need to do if we prove B. Okay, so if u1 to un calls of u, so u is equal to u1 un, then u of x is going to be equal to x1 u1 dot 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 plus and we already know, so for A, we square root of so we need to use something about the fact that 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 ui dot uj is equal to 0 if I not equal to j, and ui, the norm of ui is equal to 1. So this is what it means to be orthonormal. So we need to figure out how we can transform this. So the norm of ux is going to be equal to wait. So let's just say like let's say ux is equal to like v1 and then this is going to be, it's an m by n. This is going to be a m by n times an n by 1 is equal to m by 1. That's what I thought. So this is going to be vn. So then the norm of ux is going to be equal to square root of sum of vi squared. So what we're going to get actually though is it's going to be like x1 u1 squared or plus x2 u2 squared. So wait, but I think that if norm of some y is equal to 1, then this is going to be to square. Wait a minute. This isn't quite right though. Something is wrong. Because this is going to be a vector. UI is a vector. Oh, but this sum. Wait, no, wait. The norm of ux is equal to the square root of the sum of vi squared. And vi is equal to the vi is going to be the first element of this sum. All right, let's. So it's really xi ui1 squared is equal to vi. No, but not squared. And then the norm of v, or the norm of ux, is going to be equal to square root of, it's going to be this. It's going to be some v squared. Now we have a scalar. So the sum of vi squared is equal to a squared. I feel like I'm going about this all wrong. We're trying to show that we know these things. We know that if we think of instead like I think we know that if we have an orthonormal matrix, then no. Orthogonal matrix. All right, I think it's time to look at an answer. How are you supposed to do it? Oh. Wait, what is delta? What is this? Wait, I don't know this identity. Oh. Can we rely on this? How do we know that's true? Oh, yeah. Okay, so in our problem, which was problem 33, prove u m by n or no calls, then the norm of ux is equal to the norm of x. B, the ux dot uy is equal to x dot y. Okay, so let's see if we can get through this. So we have this theorem, which is, well, I actually want to rewrite down the proof of that. So let u equal u1, u, n. Let's just say 3. So then you get u transpose u is equal to u1 transpose u2 transpose u3 transpose. Yep. So then this is going to be equal to, this product is going to be equal to like u1 transpose u1, u1 transpose u2, u1 transpose u3, and so on. Since or no, since u is or no, this product clearly equal to the identity matrix. And this is going to be a n times m times n is equal to n. Okay, now for this proof. So ux squared is going to be equal to ux dot ux. But now they do this thing. Okay, so okay, so now that we have this, I guess then we get x transpose u transpose ux. But this becomes the identity. So then we get x transpose x, which is equal to x dot x. Which is equal to the norm of x squared. Thus, ux is equal to x. Now, the weird part about this for me was that this is a vector. But so if we have a m by n times an m times an n by 1 transpose, then we get a 1 by n times an n by m, which is equal to a 1 by n. So I think that's fine. All right, so now we got to do part B. Part B, prove for all x, y, u of x dot u of y is equal to x dot y. For u or no calls, where orno means orthonormal. Okay, so we can apply this thing again, which is our handy trick, that ux dot uy is equal to ux transpose uy, which is equal to x transpose u transpose u transpose or u y. So then this goes, and then we get x transpose y, which is equal to x dot y. All right, cool. That was a good problem. Suppose W is a subspace of Rn spanned by n non-zero orthogonal. If they're all orthogonal, then they're all independent. And there's just a theorem that says if you have n independent vectors, then it spans the thing. So that's fine. Let U be a square matrix with orthonormal columns. Explain why U is invertible. There's a theorem here. By theorem 6. So what do we need to prove? Okay, prove if U is square with orthogonals, then U is invertible. Okay, so the first theorem that I want to use is that orthonormal, wait, where did we prove it? How did we prove it again? I'm trying to say that the what I'm gonna say is that the determinant is non-zero, therefore it is invertible. If it's square and it has non-zero, well, is determinant only defined for square? I think this book has only done square determinants. I don't even know if it generalizes. But where was that problem? Was it in the last section? Am I tripping? When did we do that? I swear we just did that. I think it's in this section. Oh, it was this. Okay, the proof was didn't they use it? But this might be a circular thing by theorem 6. Okay, so first by theorem 6 we know U transpose U equals I. And we can show that the det of U transpose U is equal to 1, which is equal to det U transpose times det U is equal to 1. Since, and it's true for all matrices, right? For all mats, det A equal to det transpose A. TR could be trace, but hopefully in context it knows that I mean transpose. Okay, yeah. So then we rely on, since det U transpose equals det U, then we get det U squared equals 1, i.e. det U equals plus or minus 1. So now that we know this, so then U is square with non-zero det. Therefore, U is invertible by the invertible matrix theorem. That was a good problem. This is actually my favorite problem so far. Let U be an n by n orthogonal matrix. Show that the rows form an orthonormal basis of Rn. Wait, if it's square with ortho... Oh, yeah, it's an orthogonal matrix. Show rows of U form orno basis of Rn. Okay, how do we want to do this? So what do we know? If we have an orthogonal matrix, then we know that U to the minus 1 equals U transpose. Okay. We also know that U transpose is equal, or wait, U transpose U is equal to I. It doesn't actually matter, it's the same. So if we multiply both sides by U, then we get U inverse U is equal to U transpose U, but that just gives us that I is equal to I. So that doesn't really tell us anything, right? What are we trying to show? We're trying to show that this is an orthonormal basis. Okay, for an orthonormal basis, the definition of orthonormal basis is we need to show rows of U equal to R1 to Rn are such that that we have the norm of Ri equals to 1 and Ri dot Rj is equal to 0 if I not equal to j. So that's what it is. And I mean, this already gives us linear independence, right? But that R1 to Rn independent. Okay, so we need to figure out, so if we just think about U transpose, it's going to be equal to, oh wait, yeah. Okay, and then we're gonna try to show, so we could show that U transpose columns. So U, or rows of U are orthogonal if, and we take U transpose is equal to V. Then we have V transpose V is equal to I. So if we have U transpose times U transpose is equal to I, then U transpose has orthogonal call. This is U times UT is equal to I. We know it's invertible because it's square. I don't think they actually display it as a theorem, but it anyways, you get U transpose equals U inverse, and then you just but this is, wait, okay, what do we know? We know that U transpose U equals I. We also know that U inverse equals U transpose. That's what we know. So now we want to show U transpose U transpose is equal to I. So if we were to transpose this whole thing, then we would get Okay, I think that's enough. I think that's true. Because we were able to write that equation. Let's see how ChatGPT will answer that question. Wow, that's really concise. Okay, that's cool. Okay, 37. UV orthomats. Prove UV orthomat. So what do we know? We know that oh, shit. All right, I need to go on a walk because I'll go in a second. Yeah, no, I'm gonna go. I'll be back. Okay, so I'm back. Okay, so what do we know? We know that UV, or what do we know? We know that U transpose equals U inverse, and V transpose equals V inverse. So then U transpose V transpose is equal to actually, let's do it the other way. Let's say V transpose U transpose is equal to V inverse U inverse. So that means that UV transpose equals UV inverse. All right, so there we go. All right, I think that'll be it for this section because we got to get going. We got to do other stuff.